So let's solve some questions related to like the ratio test, how we apply it to the actual random variables. Remember we previously solved a question related to normal distribution where sigma square is known case. But in that case our hypothesis was a one-sided composite hypothesis. So here let's start with sigma square is known case again. And then we will solve also a question related to where sigma square is unknown case. It's much more complicated than this. And let's say we have a random sample of size n from normal distribution. And let's assume that we want to test that mu equal mu 0 versus two-sided alternative, mu not equal to mu 0 case. Okay, so in this case we don't have any uniform most powerful tests, but still if we want to test such a hypothesis, then we need to derive, we have to know the testing procedure. Okay, so let's derive the generalized likelihood ratio test, or just likelihood ratio test of size alpha. We may continue with the finding the power or probability of type 2 error, but let's first derive the test. Okay, so we have to define the maximum likelihood estimators under the null space and also for the whole parameter space. So our first step is finding the maximum likelihood value under the null hypothesis. So basically when we look at the null hypothesis, it only takes one value, mu equals mu 0. So the maximum point that the mu can take is just this value, right? Okay, so let's write the quantity here. So we have 1 over 2 pi sigma square n over 2 e to the minus summation xi minus mu 0 whole square divided by 2 sigma square. So this is the maximum point that the likelihood function can take under the null space. So do the same thing for the whole parameter space. Okay, so find the maximum value of the likelihood function where the range of x is between plus minus mu. So actually you know how to find the maximum likelihood estimator of normal distribution, which is x bar. But if you don't know the maximum likelihood estimator, then you have to derive the maximum likelihood estimator. Okay, so first your job is to be able to find the maximum likelihood estimator and then replace it in the likelihood function. So we already know that it is x bar. Okay, so the estimate value under the whole parameter space, the maximum likelihood estimate is x bar. So when we write it, we have 1 over 2 pi sigma square n over 2 e to the minus summation xi. Now we replace our mu by x bar, xi minus x bar whole square divided by 2 sigma square. Okay, so this is the maximum value of the likelihood function under the whole parameter space. Okay, so what is the third step is finding the ratio, right? So our lambda is the maximum value of the likelihood function under the null space over the maximum value of the likelihood function under the whole space. So we have to take the ratio of these two functions. Okay, so let's write the function. So we have 1 over 2 pi sigma square n over 2 e to the minus summation xi minus, we replace mu by mu 0 over 2 sigma square divided by 1 over 2 pi sigma square n over 2 e to the minus summation xi minus x bar whole square divided by 2 sigma square. Okay, so basically here you can so these two quantities cancels out. Okay, so to ease the calculation, what you can do, you can just open up the squares here and here, and we will have some cancellations at the end. Or you can add and subtract x bar term here, plus minus x bar term, whatever you want. So let's open up the square and then see what we will have. So e to the minus summation xi minus 2xi mu 0 plus mu 0 whole square divided by 2 sigma square. And do the same thing here. Xi minus 2 xi x bar plus x bar square divided by 2 sigma square. Okay. So what we have here, e to the minus summation xi square. So that minus sign here. Okay, then we have plus 2 and x bar mu 0 minus and mu 0 square divided by 2 sigma square. Okay, and we have e to the minus, let's put it again here, minus summation xi square plus 2 and x bar square minus and x bar square 2 sigma square. Okay, so what we have here, okay, so as you can see, these summation xi square, e to the summation xi square will cancel out. Okay, then what we have here is, okay, so we have e to the 2 and x bar mu 0 minus and mu 0 whole square 1 over 2 sigma square term here, and we have, so here if we combine these two, we will have e to the what we have, okay, so n x bar square over 2 sigma square, right? Okay, then, okay, so combine everything here. So we have e to the, so put the denominator into the numerator, putting minus sign here, and x bar square. Let's put minus here, and then we have plus 2 and x bar mu 0. And also we have minus and mu 0 square divided by 2 sigma square. As you can see, we have whole square term, e to the minus and x bar minus mu 0 whole square divided by 2 sigma square. Okay, now this is our lambda. So our generalized likelihood ratio test will be rejecting H0 if our lambda less than lambda 0. Then what's our lambda? It is e to the minus n x bar minus mu 0 whole square divided by 2 sigma square less than lambda 0. Okay, take the ln of both sides, so we have minus n x bar minus mu 0 whole square divided by 2 sigma square less than ln lambda 0. Okay. Okay. So we can keep everything in this using this statistic, or the simplified version of the statistic is just this one. So you can keep using that if you want. Okay. So so let's keep this statistic alone here. So we have a minus sign, so put the turn the direction of the inequality. So we have minus 2 sigma square ln lambda 0 over n. Okay, so what is that? So since this is in terms of squares, right? So let's say this is our k square. Okay, so now k is the unknown parameter case. In terms of a statistic, how can we define our rejection region? Then reject H0 if x bar minus mu 0 less than minus k, or x bar minus mu 0 greater than k, right? This will be our rejection region. In terms of x bar, let's write everything in terms of x bar. Then x bar should be less than mu 0 minus k to be able to reject the null hypothesis, or x bar should be greater than mu 0 plus k. So let's say this is our C1 and this is our C2. Okay? So then our job is to be able to find the values of C1 and C2. Right, so this is our unknown and this is our unknown. So to be able to define the test fully, so we have to define this. So what is the option again? Using the given information, which is the probability of type 1 error. So we know alpha at the beginning, it's given to us, or we set it as small numbers. Okay, so write the rejection region. So this is the same actually. So for all testing procedures, so definition never changes. A0 is true. Okay, so what is our rejection region? So x bar, so since it's in the probability, now it's a random variable, less than C1, given mu equal mu 0. Okay, and we have or let me put the given part later. Or oops, I didn't choose. Or x bar greater than C2 given mu equal mu 0. Then what we can do, x bar less than C1 given mu equal mu 0 plus probability that x bar greater than C2 given mu equal mu 0. So at this point we have to use the distribution of x bar, and we know that x bar is normally distributed with mean mu. Actually our mu is mu 0 in the definition of alpha, and also sigma square over n. And we know that we have a statistical table for the standardized version of that, which is that x minus mu divided by sigma over square root of n distributed as standard normal. Then we can use standard normal tables to be able to define our test, and we can find the C1 value and C2 value. Okay, so doing that, let's standardize our x bar minus, now my true mu is mu 0, right? Sigma over square root of n, less than, do the same thing here, sigma over square root of n, so mu equal mu 0, plus probability that x bar minus mu 0 divided by sigma over square root of n now greater than C2 minus mu 0 sigma over square root of n given mu equal mu 0. So now we know that this part is z, this part is z. So probability that z less than C1 minus mu 0 sigma over square root of n plus probability that z greater than C2 minus mu 0 divided by sigma square root of n. Okay, then normal distribution is symmetric, you know. So we have to so this probability is alpha. So using the symmetricity property, so this should be alpha over 2 probability, and this should be alpha over 2 probability. And let's draw our normal z. So we are talking about two regions, and with sizes tail probabilities alpha over 2, which are our rejection region. So we want to reject z when this point as C1 minus mu 0 divided by sigma over square root of n. So lower than that, we'll reject null hypothesis. So this is our threshold. And here we have C2 minus mu 0 sigma over square root of n, and this is our threshold for the upper bound. So value bigger than that will be in the rejection region. Then in terms of standard normal table, this quantity is minus z alpha over 2, you know. and this quantity in terms of normal, so we are using upper tail probability ZF/2. Since they are symmetric, we are writing that like that, but you can also define this as 1 minus, sorry, not 1 minus, Z1 minus F/2. So these are basically the same, but usually we are using the symmetric version of that. So then using that, our C1 minus mu0 divided by sigma over square root of n equals to ZF/2. So this means that our C1 should be mu0 minus ZF/2 sigma over square root of n. So this is the testing procedure that you already know from the statistical methods class. And for C2, do the same thing. So this is how we derive the test actually. So previously you didn't know how to derive the test. So this is the testing procedure, how this test and these values appears. So we have mu0 plus ZF/2 sigma over square root of n. So what is our likelihood ratio test then? Our generalized likelihood ratio test of size alpha is to reject H0 if my X bar is less than C1, which is this one. Don't write C1, so we already found it, right? Or X bar greater than mu0 plus ZF/2 sigma over square root of n. So now this is our testing procedure. This is the rejection region that we have, right? Okay, so after that, so this is the test that we have. We have a two-sided region and we found the rejection regions. And let's also, this is the end of the likelihood ratio testing procedure we already found. But let's put B, let's say the previous one it was A, and then let's find the power function. Power function, pi mu, for any mu. Let's try to define that. Okay, so what was the definition of power function? It is the reject probability of reject H0 for mu, mostly under the alternative. Oops, where is it? Nereye gitti? Okay, sorry. It automatically goes somewhere. Okay. Okay. So what was that probability that rejects H0 for any mu? Okay. So then write the test. Don't write C1 or C2 anymore. So X bar less than mu0 minus ZF/2 sigma over square root of n given mu plus, for the upper bound, do the same. Now my mu is not mu0 anymore. Okay, so other mu. So then I have to standardize my random variable X bar by new mu, not mu0. So probability that X bar minus mu sigma over square root of n, and do the same thing here. Okay, so I have mu0 minus ZF/2 sigma over square root of n minus mu divided by sigma over square root of n given mu plus probability that X bar minus mu, again I'm using mu, my true mu is mu right now, not mu0, and we have mu0 plus ZF/2 sigma over square root of n minus mu divided by sigma over square root of n and mu. Then our power function will be, so now we have z here. Okay, so we have some cancellations. Oops, not greater than, sorry. It should be less than. Less than. Okay, so what we have here is mu0 minus mu sigma over square root of n and minus ZI over 2 plus probability that Z greater than, so we have mu 0 minus mu sigma over square root of n plus Zi over 2 now. So this is the power function. Mu 0 is coming from the hypothesis at the beginning. So we already know sigma. We know the sample size. Alpha is already given. And for any given mu value, I can calculate this probability by using the standard normal table. Okay. Okay, so let me stop here, and I will also solve a question related to normal distribution, where now sigma square is unknown. It's much more complicated than this, because under the null and under the alternative we have to find the maximum likelihood estimators for sigma square also, because those are unknown. Okay, so let's continue with the normal in another video.